Imagine this, you're a detective in a foggy city. You're hunting an invisible killer that's everywhere. PM2.5. These tiny particles, which are 30 times thinner than a human hair, can sneak into your lungs and bloodstream, causing heart disease, respiratory problems, and even premature death. Every year, they kill millions of people around the world. It's a quiet assassin in the air we all breathe. Who will be our only on-the-ground witness? Air quality sensors, but they are spread thin. And in many places, they are missing entirely. Then, how can we investigate PM2.5 more effectively? Let's dive in. Ground-based monitors track PM2.5 directly, but they are like scattered witnesses, reliable where present, yet woefully sparse. These stations leave massive blind spots in our exposure map across vast regions, especially across bustling East Asia. It is like trying to solve a jigsaw puzzle with half the pieces gone forever. Are there any other instruments available for monitoring PM2.5? Then, the aerial spies arrive. Satellites. They don't measure PM2.5 directly, but they do detect something called aerosol optical depth, or AOD. It measures how much sunlight aerosols block or scatter. A greater AOD means more sunlight is being absorbed or deflected, signifying a high concentration of aerosols in a specific region. In contrast, a smaller AOD indicates a lower aerosol concentration, allowing more sunlight to reach the ground without being absorbed or scattered by the particulate matter. Think of AOD as a shadow cast by all airborne particles, with PM2.5 as the prime suspect hiding inside. AOD gives a bird's-eye view of the total aerosol load. It often lines up with ground-level PM2.5. But not perfectly. Aerosols stack vertically like a layered cake, some ride high, others hug the ground. Interpreting surface PM2.5 from AOD is like trying to guess the ingredients of the cake merely by looking at its surface. While you might get a sense of its appearance, the true essence and complexity of the flavors remain hidden beneath the frosting. There are uncertainties involved. However, if we can crack this code, we can turn skyward eyes into surface truth. Most satellites revolve around Earth and only snap a region once or twice a day. Not enough for a live investigation. Geostationary satellites deliver the breakthrough. Hovering 36,000 kilometers above the equator, they orbit in sync with Earth's spin. It is like stakeout pros locked on one region. This fixed gaze delivers images every 10 to 15 minutes with full disk coverage and zero blind spots. A powerful geocluster, including the Geostationary Ocean Color Imager, GEOS-CHEM, the Advanced Himawari Imager, AHI, and other sensors, stitches overlapping views into a continuous, high-definition live stream. Pollution spikes. They catch it as it happens. This is our new leader from guessing to real-time HD. To fully utilize the satellite measurement, we have to decode the PM2.5 AOD link. Therefore, we turn to our chemical transport model, GEOS-CHEM, to do the job for us. But our investigation hits a snag and fails to reproduce the air pollution issues East Asia is facing. Fortunately, Korean aircraft from the KOR-USAQ campaign flew through real haze, providing invaluable measurements of aerosol properties in East Asia. The aircraft data revealed the flaw in the simulation. The model underestimated the aerosol size distribution. But why? The default settings were tuned for North America. East Asia has a heavier industry and a different climate, so those parameters did not apply to it. It was like using a Los Angeles air quality app to forecast Beijing smog. In light of this, we recalibrated particle size parameters to reflect East Asia's reality. And the result? GEOS-CHEM now matches satellite AOD patterns, pixel for pixel, across space, strength, and seasons. The link between AOD and PM2.5 came into striking spotlight. It's a giant leap toward using satellite data for full coverage, real-time PM2.5 assessments, and no more patchy maps. And here's the beautiful part of natural science. These tiny tweaks ripple out to regional impacts, improving forecasts for millions. Tiny interactions shape our world. However, the case isn't closed. Aerosol size isn't the only suspect. Factors like relative humidity can swell particles, messing with AOD readings. We need more sensitivity tests to figure out how these play out. So, fellow detectives, grab your magnifying glass and dive into the full study conducted by Professor Zhai from the Department of Earth and Environmental Sciences at the Chinese University of Hong Kong. Check the link in the description box below. The mystery has not yet been solved, but together, we're clearing the air. Thanks for watching. Bye-bye.